Question 6 says the figure represents a snapshot at time t equal to 0 of transverse sine wave traveling in a string in the positive x direction. If the angular frequency of the wave is 100 radian per second, then the velocity of point marked A at this instant is, and the four options are given, and this is the snapshot at t equal to 0. Well, looking at the snapshot, we can write its equation and we can call it y t equal to 0, x t equal to 0, and for this part we have, well, the maximum value is 5 mm, so it's 5 mm. It's sine kx, and k is 2 pi by lambda, the wave number, and we can see that, well, the lambda we cannot figure out from the graph itself, so let it be 5 mm sine 2 pi by lambda into x. We can see that it will match if you look at the values of y versus x and also the slope. This is matching. Now this is y at t equal to 0 as a function of x. Now since the wave is traveling in the positive x direction, and let's say it is traveling with speed v, then the equation y xt can be written as y t equal to 0 x minus vt, and this can be written as 5 mm sine 2 pi by lambda, and instead of x we put x minus vt. This is in fact the equation of the wave, and to find the particle velocity, expression will be vp is equal to del y by del t, and that is equal to 5 mm into 2 pi by lambda into v. In fact it is minus v, so it's minus v, cos 2 pi by lambda into x minus vt. This is the particle velocity, and we are talking about time t equal to 0. So at time t equal to 0 we have to find the particle velocity, and we further look here and see that the value of y there is 2.5 mm, which means we can take this entire thing as 1 by 2, and that further means that we can take the value of 2 pi by lambda x, since we are talking about t equal to 0, this as equal to pi by 6. Again, considering the value of the sine function as well as the slope, both taken together, this value is pi by 6, and so the particle velocity now we have, and this particle velocity is equal to, we have in fact 10. Let's further 2 pi by lambda is k, and we know that v is equal to omega by k. Since omega has been given to us, so v into k can be replaced by omega, so we have vp, particle velocity, is equal to minus 5 into omega, and cos pi by 6 would be root 3 by 2, and this of course is in mm. The unit not mentioned is mm, and we shall also put the value of omega to finally get the particle velocity. If I put the value of omega, which is 100 radian per second, well, this is coming out to be minus 500 by 2 root 3 millimeter per second, which is minus 250 root 3 millimeter per second. That's the particle velocity, and in vector notation, well, we can see that this is equal to minus 250 root 3 j cap millimeter per second. So that is the particle velocity of point A at t equal to 0, and among the options we can see that this is matching with option 3. So option 3 is correct. Let's go to the next problem now. Question 7 says a uniform sphere of mass m and radius r has a thin tunnel along its diameter. A particle of mass small m, very small compared to capital M, is released from rest into the tunnel at the surface of the sphere. If the particle moves under gravitational force of the sphere, then the minimum time it will take to reach the center of the sphere is. As far as concepts are concerned, it involves concepts of gravitation as well as SHM, and we know that if a sphere is taken and if we dig a small tunnel through a large sphere and drop a particle from here, the particle is going to perform SHM. Let's find the expression for that SHM, and well, the time taken, if the time period is t, the minimum time it will take to reach the center will be t by 4. So to find the time period, let's find the restoring force on the particle when it's at distance small r from the center. And let's assume, of course, it's given in fact that the radius of the sphere is capital R. So when the particle is here at distance small r from the center of the sphere, the restoring force F is coming out to be minus capital G and well, mass of the sphere m into small r cube by capital R cube. This in fact is the mass contained within the sphere of radius small r, and into small m by r square. This is the expression for the gravitational force. This also is the expression for the restoring force. So that means we can now write small m into d2r by dt square is coming out to be equal to minus g capital M small m r by capital R cube, and this means that d2r by dt square is minus capital G capital M small m goes off on both sides into small r by R cube. So we have the differential equation for the SHM. The value of omega will be under root of G capital M by R cube. And we have to find the time it will take to reach the center of the sphere. So that time is t by 4, where t is the time period. That means it is 1 by 4 into 2 pi by omega. So let's put the value of 2 pi by omega, and then this is coming out to be under root R cube by Gm. So this simplifies to pi by 2 under root R cube by Gm. So this is the expression that we are getting for the time taken. Among the options, we can see that it is matching with option 4. So option 4 is correct for question 7. Let's go to the next problem now. Question 8 says the damping coefficient of a damped simple harmonic oscillator of mass 1 kg is 10 to the power minus 2 SI units. Time after which the amplitude of the oscillator becomes 1 by 10 of its initial value is. Well, it's a case of damped oscillation, and well, we know that amplitude as a function of time in this particular case can be written as A t is equal to initial amplitude A naught e to the power minus bt by 2m, where b is the damping coefficient. So in our case, A is A naught by 10. So let's plug in the values. We have A naught by 10 is equal to A naught e to the power minus bt by 2m, and well, b is given as 10 to the power minus 2. So it's minus 10 to the power minus 2 t divided by 2m. The value of m is 1 kg, so it's simply 2 here. So this means that we have 10 is equal to e to the power 10 to the power minus 2t by 2, and if we take log on both sides, we get ln 10 is equal to 10 to the power minus 2t by 2. This in fact gives us the value of t, and the value of t is then 200 into ln 10 second, and this is matching with option 4. So option 4 is correct for question 8. Let's go to the next problem now. Question 9 says a thin non-uniform rod of length L has linear density lambda equal to kx, where k is a constant and x is the distance from the top end. The rod is hinged at its top end from the ceiling of a lift which has an upward acceleration of g by 2. The time period of small oscillation of the rod in the frame of the lift would be. So this is a lift which is accelerating upward with acceleration g by 2, and it's a non-uniform rod whose linear density varies as kx, where x is the distance from the top end. We have to now find the time period for small oscillation of the rod in the frame of the lift. Well, the question involves multiple concepts. We need to find moment of inertia, we need to locate center of mass, and we need to apply the equation, or rather the formula, time period t is equal to 2 pi root I by mg effective into d. So I is the moment of inertia. Now about axis which is passing through one end of the rod, we have to also find the expression for mass and d. All these calculations need to be done. As far as g effective is concerned, well, g effective will be 3g by 2 because the lift has acceleration g by 2 upward. So let's start with I. I is then integral r square dm, and well, r square dm will become x square. Dm will be kx dx. That means we are considering x distance from top and taking element of length dx. This distance is x, and the value of x will go from 0 to L. So this will come out to be equal to kL to the power 4 divided by 4. That is I. Let's find the mass of the rod, and the mass of the rod is integral lambda dx. Again, lambda is kx, so it is kx dx. X goes from 0 to L. This is giving us kL square by 2. That is m, mass of the rod. And finally, to find d, let's locate the center of mass of the rod. And well, if I call it axiom, in fact axiom will also be equal to d, is integral x dm, which is x into kx dx. That means kx square dx, and again x goes from 0 to L, divided by total mass. The total mass we have already found, and that is kL square by 2. So let's simplify this now. So k goes off, we have LQ by 3. So well, a 2 will come here, and this will simplify to 2L by 3. That is axiom, and this is also in fact d, the distance of the center of mass from the point of suspension. So now we can plug in all the values to find the time period, and that time period t will be 2 pi under root I. The value of I is kL to the power 4 by 4. So it is kL to the power 4 by 4. This is, and then m is kL square by 2. So it is kL square by 2, and g effective is 3g by 2. So it is 3g by 2, and d is 2L by 3. So it is again 2L. Well, the time period is 2 pi. I is kL to the power 4 by 4, m is kL square by 2, g effective is 3g by 2, and finally d is 2L by 3. Let's now simplify this to find the time period. This is coming out to be 2 pi under root of, well, k will go off, and we have this 3 also goes off. So this is then L by 2g. This is the time period, and well, if we bring in this 2 under the radical sign, the time period is coming out to be pi under root of 4L by 2g. That means 2L by g. And if we look at the options, it is matching with option 4. So option 4 is correct for question 9. Let's go to the next question now. Question 10 says the potential energy U of a particle of mass m depends on its position x, as U is equal to 2 minus cos ax, where a is a positive constant. The time period of the particle for small oscillations is, and these are the 4 expressions. So what we do is we make use of the concepts of conservative force and potential energy function. The conservative force F is given as minus du by dr. In this particular case it is minus du by dx, because potential energy varies with x here. And if I carry out this derivative, well, it is minus. So finally it will be minus a sine ax. And for small values of x, we can replace this by minus a into ax. That means minus a square x. This becomes our restoring force for the SHM. And on the left hand side is mass of the particle, m d2x by dt square. So by replacing sine ax by ax, we have the equation for the oscillation as d2x by dt square is minus a square by m into x, and this gives us the value of omega as under root of a square by m, and the time period as 2 pi by omega, or 2 pi under root m by a square. So time period if I take this A outside, it is 2 pi by A under root M. And if we look at the options, we can see that it is matching with option 3. So option 3 is correct for question 10. Let's go to the next question now.